Recording has started.
Let's take a look and see how you're doing so far on these. So for number one, we may or may not need them, but the first thing I'm going to do is find some missing dimensions. And the first thing I'm going to do is I'm going to find the total height of this thing, which is just the 8 plus the 10 plus the 9. Those three dimensions add up to the full height, which comes out to be 27 inches. From that full height, I know that this piece over here then has to be 24 inches because the 3 and that piece have to add up to 27. Next, I'm going to find my full length here, which is 4 plus 16 plus 6, which adds up to 26 inches. And then again, I know this piece right here with the 10 has to add up to 26. So that's a 16-inch piece. So now to find the area of this, I have some options. I can cut it into little rectangles and add them together. Or I can fill in the missing pieces and back out the missing pieces later. Yeah, it looks like the easiest way to go about this one is I'm going to fill in those corners. Now I have a big rectangle that's 26 by 27. That gives us an area of, what is it, 702 square inches. Now then we have to subtract out the missing pieces. This piece here is 4 by 3. That's 12 square inches. This piece here is 6 by 8. 48 square inches. And this piece up here is 9 by 10. 90 square inches. 150 square inches. It has to be subtracted back out. So we get a total of 552 square inches of area for that shape. How many of you had that one correct? Cool. Any questions on it? 3 and 4 here are actually very closely related, as I'm sure you saw. Number 3, I have a rectangle here that is 16 feet long. The trick is figuring out this width here. Well, I know that this length here has to be half of the difference between the 16 and 24. 24 minus 16 is 8 feet. So this has to be 4 feet here and 4 feet here. Well, that 4-foot radius turns into an 8-foot diameter. 16 feet by 8 feet or 128 square feet. Now for the rest of that, I have 2 half circles, but there is nothing that's saying that I can't take those 2 half circles, take them apart, and then put them back together to make one full circle, the radius of 4 feet. So that's what I'm going to do is rather than doing 2 half circles, I'll make one full circle. Pi times 4 squared, which is 50.24 square feet. Giving me an area 178.24 square feet. Number 3 uses the exact same pieces. We have the big rectangle here that is 128 square feet. And we have the circle that's an 8-foot diameter or 4-foot radius. It's 50.24 square feet. The difference is here, the circle is not added onto the rectangle. It's cut out from the rectangle. It's subtracted. So that gives us 77.76. Number four. Number four brings us back to our rule of triangles that we discovered yesterday. Hero's formula or Heron's formula, depending on how you want to pronounce it, where we can find the area of a triangle simply by knowing all three sides. Most area formulas, we have to have two perpendicular dimensions to do it. So we start out by finding the perimeter. 6 inches plus 13 inches plus 17 inches. Perimeter. From that, we find the semi-perimeter, which is half the perimeter. The 36 inches divided by 2 is 18 inches for the semi-perimeter. So now the area is the square root of that semi-perimeter times the semi-perimeter minus the shortest side times the semi-perimeter minus the second longest side times the semi-perimeter minus the longest side. So this will be the square root of 18 times 18 minus 6 is 12, 18 minus 13 is 5, and 18 minus 17 is 1. Square root of 18 times 12 times 5 times 1, 32.86. Those units were in inches, so this is in inches squared. Any questions there? So today we're going to continue dealing with areas, but we're going to also talk a little bit more about perimeters. Now for number one here, the perimeter would be pretty easy to find. We found all those lengths. We just have to add up 16 plus 9 plus 10 plus 10 plus 6 plus 8 plus 16 plus 3 plus 4 plus 24. We would just add all those up to find a perimeter. Pretty simple. Number four, we already did find the perimeter. That was part of that Hero's formulas. You have to find the perimeter. But let's look at the perimeter for numbers 2 and 3. So for number 3, or number 2 here actually it was, we said we had a rectangle with 2 circles on the end. Well, when I'm looking for perimeter, all I'm looking at is the actual edge pieces. So I have an edge piece here that is 16 feet. I have to find the length around this arc here. I know this edge is 16 feet. I have to find the length around this arc here. So for my perimeter, I have 2 16-foot pieces added together, plus that arc. Just like we did for area, I'm going to take those 2 half circles and put them together to make one full circle. And we found up above that that has a diameter of 8 feet. The circumference of that full circle is pi times 8 feet, 25.12 feet. So for our perimeter, we add those together, giving us 57.12 feet of perimeter. For number 3 up above, we had 16 feet total height there, and an 8-foot gap in between the 2 half circles, the 2 arcs. Well, we have a 16-foot piece here and a 16-foot piece here. And we have those two half circles there that we could pull apart and make a full circle again. And again, that diameter is 8 feet. That circumference is just pi times 8 feet at 25.12 feet. Or 57.12 feet of total perimeter for that shape. So for these two, because it's the same two shapes that are put together in different ways, the perimeter stays the same. The area changes because in this one down here, the half circular pieces are cut out instead of added on, but they still add the same to the edge of that shape. Well, another application of this, look at trapezoids. Right now, we have enough information to find the perimeter and the area of this trapezoid. Well, I shouldn't say that. We don't quite have the information yet. Let me do this. Now we have the information to find both the perimeter and the area of this trapezoid, based on just what we learned yesterday. We'll give you a minute to kind of look it over, and don't necessarily do it in your notes, but see if you can come up with a game plan of what we're about to do. Anytime we see a right triangle, and we see that we have two of the sides, we should instantly see that, well, we know the third side, or we can find the third side rather quickly because of that Pythagorean theorem. A squared plus b squared equals c squared. And we have a right triangle down here on the left. We have one of the legs, the 6-inch leg. The other leg would be the height of that triangle. The 10-inch side is our hypotenuse. Got a squared plus, we'll put 6 in for b, so that's 6 squared equals 10 for c, makes that 10 squared. A squared plus 6 squared is 36. 10 squared is 100. We're going to subtract 36 to get a squared equals 64. And then we'll square root. A equals 8. This is 8 inches here. Well, since we told you this is a trapezoid, that means the 12-inch base and the 33-inch, that should probably be inches, not feet down there. The 12-inch base and the 33-inch base have to be parallel. In order to be bases of a trapezoid, they have to be parallel to each other, which means the distance between them is constant. One of the definitions of parallel is always the same distance apart, or everywhere equidistant is the technical terminology. So that means this is 8 inches apart over here as well. I know this as the opposite side of a rectangle has to be 12 inches, has to be same as that top side of the piece. So I have 6 and 12, that adds up to 18. I need another 15 inches to finish off that 33 inches. So this piece here has to be 15 inches. Well, once again, I have a right triangle where I have 2 of the sides and not the third one. So if I call that side C up there, call this A and B. So A will be 8, so that'll be 8 squared. B will be 15, so that'll be 15 squared equals, we're looking for side C, so that's C squared. 8 squared is 64. 15 squared is 225. Add those together. 64 plus 225 is 289. Equals C squared. Now we're going to square root those. So 17 equals C. So that's telling us that side C up here is 17 inches. So to find perimeter, let's do that first. We just pick a spot to start, and we add up sides. So I'm going to start right here. This whole side here is 33. I'm not going to worry about the little pieces. I know the whole thing is 33. So I'm going to take that whole big thing. This is 17 inches. 12 inches. This is 10 inches, which brings us back to our starting spot. So that's it. Add all those up. What do we have? 72 inches. A perimeter. For area, we have 1, 2, 3 pieces there. Piece 1 is that right triangle that's 6 by 8 inches. 48 inches squared. Piece 2 is that rectangle that's 12 by 8. Oops, what did I do wrong there on that first piece? Triangle, so I had to divide by 2. 24 inches squared. That second piece is a rectangle that's 12 by 8. That's 96 inches squared. And the third piece here is this triangle that is 15 by 8. And of course, because it's a triangle, we have to divide it in half. Gives us 60 square inches. For a total of 180 square inches of area for that whole trapezoid. So that Pythagorean theorem, a squared plus b squared equals c squared, that we learned yesterday, is an extremely powerful rule. Being able to find, there's so many things in geometry that have right angles in them that can be turned into right triangles. Being able to find a missing side, if we know 2 of them, it occurs a lot. Next, let's look at something a little bit different. Let's look at something that doesn't have straight sides. So we talked about circles here a couple days ago. And of course, we talked about, let's say we know the diameter of that circle is 16 millimeters. From that, we know a lot of other things. First of all, we know the radius is half of the diameter. Technically, we know the diameter is 2 times the radius, so going the other way, you divide by 2. We know that the circumference is pi times the diameter. So that would be pi times 16 millimeters, giving us 50.24 millimeters. And we know the area is pi times radius squared. So pi times 8 squared here, 64 squared, so 200.96 millimeters squared for area. We've looked at half circles and quarter circles. If that's a quarter circle, that piece is what's referred to as a sector. The area of a sector is just what we've been doing. It's that fraction of a circle. But rather than looking at it as divided by 4, for area of a sector, I do area, then I draw a little sector down below it like that. That means area of a sector. I have the area of my full circle at 20.96 millimeters squared. And the last couple of days, we've just been dividing that by 4 because it's 1/4 of a circle. But today, we're going to use a little bit more general formula. This is 90 degrees. It's a right angle. The full circle is 360 degrees. So that sector is 93/60ths of a full circle. Or 50.24 square millimeters. So that means is we're no longer restricted to half a circle or 1/4 of a circle or any of those anymore. If I have a sector of a circle here, I know it's a sector because those two sides are the same, so that makes them radii. And I know the angle here, let's call that 20 degrees. To find that, I find the area of a full circle. So A with the full circle down there, that means the area of the full circle, is pi times 10 squared, which is 314 square feet. So then the area of that sector is that full circle, 314 square feet, times the fraction of a full circle. That is 20 degrees out of 360 degrees. 314 times 20 divided by 360. Give us 17.44 square feet of area for that sector. Excuse me. So let's go back to that circle that was 16 millimeters for diameter. Our circumference was, again, pi times 16, or 50.24 millimeters. If I had a quarter of that circle, and I wanted to find that length, that is called an arc, by the way. Any portion of the outside edge of the circle, any portion of the circumference of the circle, is an arc. Find that arc length. Yes, the last couple of days we've taken the full circumference, 50.24, and we've divided it by 4 because it was 1/4 of a circle. But again, let's do something similar to what we did with the sector area. That's 90 degrees, is this angle here. Out of, it would be 360 degrees for the full circle. Notice that 90 over 360 is 1/4. Giving us 12.56 millimeters is that arc length. Let's go back to this one where we had 10-foot radii and a 20-degree angle. To find that arc length, just all we're talking about is this piece here. We have to find the circumference of the full circle. Pi times 20 feet, because the 10 is just a radius, we have to use 20. the diameter, which is 62.8 feet circumference. So for the arc length, we take that full circumference, 62.8 feet, times 20 degrees out of 360. That is 23/60ths of a full circle. Give us 3.49 feet of arc length. Well, this is an extremely powerful tool that allows us to find any fraction of the arc of a circle or the area of a circle, as long as we know this central angle in here, which in this case, of course, was the 20 degrees. It also allows us to find something called a segment of a circle. This piece here that I'm coloring in here is called a segment. A line segment that has its endpoints on the circle is referred to as a chord. A segment is the piece of the circle that's cut off outside of the chord, away from the center of the circle. So let's take a look at this, and let's say that we know that this is 4 feet here, 4 feet here. Of course, the radii have to be the same. Let's say we also know that's 4 feet. Let's find the area of the segment. The area of a segment is found by taking a sector area minus the area of a triangle. Well, right now, it doesn't look like we have enough information, but we do. This triangle we'll put the A in there. This triangle has all 3 sides the same, which makes it an equilateral triangle, which means all of the angles have to be 60 degrees. The one that we really care about is this one in the center here. That one's 60 degrees. So that tells us we can find the area of that sector. By finding the area of the whole circle. 3 pi times 4 squared, 50.12 square feet. And then, of course, multiplying that to get the sector area. By 60 degrees over 360 degrees. Giving us 8.35 square feet. So we now know the area of the whole sector. What that is this piece all the way out here. It includes the segment, but it also includes this triangle in here. That area we need to subtract back out. So to find the area of the triangle, we do not have a base in the height, but we do have all 3 sides. The perimeter of that is 12 feet. Just 4 plus 4 plus 4. So the semi-perimeter is 6 feet. Which will make the area 6 times 6 minus 4 times 6 minus 4 times 6 minus 4, since all three sides are 4 feet. Giving us 6.93 square feet for that triangle. Again, what we found there was this triangle in here. So to find the area of that segment, it's the area of that sector. 8.35 square feet, the whole pie wedge, minus the area of that triangle, 6.93 square feet. Giving us 1.42 square feet as the segment area. That's one of the more difficult areas that we will calculate, is the area of a segment. It's not necessarily a pleasant calculation. As we go through the next several weeks here, we will come up with strategies that make some of those areas a little easier to do. Next semester, when we talk about trig, there's a lot of things in trigonometry that make that easier to do as well. Our last thing we want to cover today deals with those arcs and those chords. So pretend that looks like a circle. That is a chord of my circle. It connects, it's a line segment that has its endpoints on the circle. That is another chord of the circle. Notice they intersect at a point. When two chords within the same circle intersect, they divide each other into pieces. Let's say that this first chord here has two pieces, 4 inches and 9 inches. The other chord, if I know one of the pieces of the other chord, I'll know both of them. If I know this piece is 3 inches, I can find this piece here. I'll call it X for now. Because within a circle, if two chords intersect, they cut each other into pieces that have the same products. Remember, product is the result of a multiplication. So the first chord has pieces of 4 inches and 9 inches. That's a product, by the way, of 36 square inches. The second chord has pieces of 3 inches and X inches. X has to be 12 inches so that they will multiply to make 36 square inches. So I know that this missing piece here has to be 12 inches. Now, general chords intersecting in a circle like that are not terribly useful. But if you have a shaft, and you're going to be cutting a flat piece on that shaft, let's say that this is 20 millimeter diameter shaft, and we know this flat section that we're cutting across here needs to be 12 millimeters. We know this has to be 10 millimeters, just half of our 20. we know that if we cut that, one of our rules of chords is if we draw in a line from the center out perpendicular to the chord, it cuts it in half. That would make that half 6 millimeters, half of the 12. We could find this length here. I called that A. Again, it's A squared plus B squared would be the 6 equals C squared would be the 10. That figures out to be 8 millimeters. So that ends up being 10 minus 8, or 2 millimeters deep, that cut to cut that flat surface. But what if, rather than being given the radius or the diameter of the stock, what if we are told that what we want is we want that flat surface, and we want that flat surface to be 16 millimeters long, and we want it to come in 4 millimeters from the edge of the shaft. We need to know what size shaft this is. We need to find the radius of this shaft. Well, we can use the rule that we were just looking at, combined with what we saw over here, that 4 millimeters there. If I draw this the rest of the way in, what I have here is a diameter. I know that's going to, if that hits that chord at a right angle at a perpendicular, it's going to cut it in half. So that 16 millimeters is cut into 8 millimeters and 8 millimeters. I'm going to call this piece here that I extended down X for now. I know that 8 and 8 are the pieces of the same chord. Well, the X and the 4 also make a chord. 8 times 8 is 64. If I divide by the 4, I get that 16 equals X. X is 16 millimeters here, which means our diameter is 16 plus 4, or 20 millimeters. And our radius, of course, if the diameter is 20, is 10 millimeters. That little formula, the equal chords, or chords of a circle that cut each other, come out to an equal product, is powerful for things like this. In construction, which takes the same course, you have arched doorways, where you might know the distance across the doorway is 36 inches, and the rise of the arch is 6 inches. You can use this then to find what radius of a circle do you need to strike that arc, to draw that arc. There's all sorts of applications for that little rule. Okay, so for now, that packet that we had posted yesterday, we're going to continue on in there. Page 156 and 157 is about rectangles, parallelograms, and trapezoids. And page 165 through 168 has problems on parts of a circle. So again, if you've got 7 minutes or so to get started on that, if you'd like to work on that, I'll be on the network here to answer any questions.